Hello everyone, welcome to the lecture on Maxwell Boltzmann statistics. Let us consider a system uh, with particles which it has particles which are identical and distinguishable. Let the number of particles in the system be n, and the volume of the system it is fixed, that is V, and U is the total amount of energy available in the system that we are considering. So now here, as the volume is constant, the energy levels available in the system, they are also fixed. So now using both Maxwell-Boltzmann statistics, we are going to derive and find the range of energies available within the system. So what range of energies are available in this given system, and how many particles are there at each energy level. Like for example, let us consider a energy level E1. So using Maxwell-Boltzmann statistics, we can find out how many particles are there at that energy level E1. So let the different energy levels in the system be E0, E1, E2, and so on up to ER. Now, so we don't know how many particles are there at each energy level. Using Maxwell-Boltzmann statistics, we are going to find that. So here let us assume that N0, N1, N2, N3, so on up to N0 be the number of particles at energy levels E0, E1, and so on up to ER. So these we are assuming as taking a particular variable N0, N1, N2, so on up to NR. Now, so N0 number of particles are present at E0, N1 is present at E1, and so on up to NR number of particles are present at ER. So, using Maxwell-Boltzmann statistics, we have to find what is N0 and what is N1, N2, and so forth. So, the equilibrium state will be the most probable microstate of the system. So, the system continuously changes, and we can the state of the system, the probability of that particular state uh, we can find, and among all the probable microstates, the equilibrium state will have more probability. So the probability of occurrence of equilibrium will be more than any other state of the system. So here, number of ways of attaining a given microstate. So how many ways we can attain a given microstate, that is given by n factorial by this n naught factorial, n1 factorial, and so on up to n naught factorial. So we have considered previously that n is the total number of particles present in the system, whereas n naught, n1, n2, and so on up to nr, these are number of particles present at energy levels E naught, E1, E2, E3, so on up to ER respectively. Now here for a given microstate, these N naught, N1, N2, N3, so on up to NR, these remains fixed for another. These remain fixed for a given microstate, and if the microstate changes, then these numbers also will be changing for that particular energy levels. So now when we apply log on both sides of the above equation, we end up getting in this logarithmic relationship. Ln of a by b is ln a minus ln b, and here using Stirling's approximation, and for so whenever we apply Stirling's approximation for large numbers, the error will be negligible. So the energy will be negligible here because n is very large. So when we apply Stirling's approximation, ln x factorial will be x ln x minus x. So here ln is natural logarithm, that is log base e. So it will expand in this way. Now here, so expanding the terms. we are representing this. We are representing this N naught and N1. We are representing this N naught and N1 by this I, and we are ranging I is equal to 0 to R. So now the only variable is in this, we know that this is constant, and N is constant because the total number of particles in the system is constant. The only variable is Ni. And if omega is maximum, then ln omega will also be maximum, because it is proportional. Like as omega increases, ln omega also will be increasing. So here the maximum value of so if we can find the condition related to ln omega, then that condition also applies to omega. Therefore will be therefore when we differentiate d by d omega of ln omega, we get the condition for Ni. So here, when we do that, we get this particular condition here. So this is what we get. Then, uh, so this, that is the sum of the changes in N naught N. So here, this is second condition. From here we get this second condition, and this condition we get from this feature of the system, that is sum of the changes is fixed. Like suppose at one energy level the number of particles increased, then at another energy level the number of particles will be reduced, because the total number of particles will be constant. So the sum of changes will be 0. That is represented by third equation. And now as total energy of the system is fixed, that is uh, a particular energy level into the number of particles that are changed, they either increased or decreased. When we multiply, it has to be 0, because the total energy of the system is fixed. So if suppose 5 particles has gained, 5 particles went to high energy state, then that must be compensated by other particles coming to low energy state. And so that the total energy of uh, distributed by the change in the number of particles, that will be 0 here. So now we have got three conditions here. The first one we got that if omega is maximum, so all that we are doing is because to find the most probable state. At most probable state, omega will be maximum. When omega is maximum, then ln omega also will be maximum. So here, if we find the condition for this ln omega being maximum, then that applies to omega also. So when we differentiate this to 0, then we get the condition for maximum. So at maximum value of ln omega, this will equals to 0. So here we are differentiating this equation 1. And when we do that and simplify, we are going to get this second condition. And third condition, it is different. It is it is based on the system. That is the sum of the changes is sum of the changes in n naught n n2 n3 so on up to n naught is 0. That is if at a particular energy level some particles are decreased, those particles will be allotted to another energy levels, because the total number of particles are constant. This condition we got from this. And the next condition we got from the total energy of the system is fixed. That is ei represent different energy levels from I equal to 0 to R, that is E naught, E1, E2, so on up to ER. And dni represents the change in the number of particles at that particular energy level. For example, at I is equal to 0, so sorry, n equal n naught, n1, so that particular the number of particle changes at that particular energy level, that gives us this condition. Now here, so here equation 2, this is subjected to third and fourth. So this is applicable. This second equation is applicable with the constraints of third and fourth. So it cannot exist by overruling these third and fourth equation. It is subject to the third and fourth. Hence, it can be solved by Lagrange method of undetermined multipliers. So here, when we multiply equation 3 by alpha and equation 4 by beta, and then add second, third, and fourth equation. So here we are multiplying. So here we are multiplying this equation with alpha and beta, the fourth equation, and then adding all three equations. So that will give us in this way, and we are taking dni common. Now dni may or may not be zero, because the number of particles that are changing at different energy levels for different microstates may or may not be zero. So in that case, if this is not zero, then this must be zero. So when we solve it, we end up getting Ni. So now here we are able to find Ni, which is e power minus alpha plus beta Ei. So here Ni is nothing but it ranges from I equal to 0 to R. So there is a condition like N naught. So for N naught, it is e power minus alpha plus beta I is 0. So E naught. So in that way, Ni is the number of molecules at ith energy level. Now here alpha, gamma, beta are constants. So Ei is the energy of ith energy level. So the number of particles present at a particular energy level depends on its energy. As you can see the relation Ni and Ei here. Now, when we see the sum of total particles is n constant, that is n naught plus n1 plus n2 so on up to nr. If we do add them, that will be n. And we know what is ni, so substituting ni here and taking e power minus alpha common. So here beta ei, so I is equal to 0 to r and n. This will give us in this form, which will be is equal to n by p. Actually, this is represented by p, which is nothing but partition function. So basically, this partition function p is constant because ei is constant. The energy levels are fixed. So what we will get, beta is a constant, ei is also a constant. So this is n by p. Now from phi here, ni is equal to e power minus alpha into e power minus beta ei. So here, this is phi. Now ni is equal to, when we separate the terms, e power minus alpha and e power minus beta ei. Now here we can represent, here we can replace e power minus beta ei with this one. So here n by, sorry, replacing e power minus alpha by n by p and writing as it is e power minus beta ei. Here p is equal to sigma is equal to 0 to r. E power minus beta is a partition function, and beta is equal to 1 by kbt, where kb is Boltzmann constant and T is temperature. So when we substitute that, we get Ni is equal to n by p into e power minus ei by kbt. So now you can see the relation between Ni and so Ni depends on the energy. Here N is number of particles constant, P is partition function, this is constant. So Ni directly relates to the energy, that is number of particles present at energy levels is related to that energy level, and it is exponentially reduces. Suppose as Ei is more, the number of particles at that particular energy level will be less. So this is the Maxwell-Boltzmann statistics. So here, based on this equation, you can see that energy is on x-axis. So here EI is the energy and the relative number of particles, that is Ni is the number of particles. So this is how we got the number. This is how we got the manner in which energy is distributed among the particles is the result of this distribution, and this reflects directly on the translational kinetic energy of the particles, the average translational kinetic energy of the particles, and the kinds of behavior the particles show with respect to specific heat. So this distribution is very applicable for particles that obey, uh, you know, ideal gas laws. So this is the end of this lecture. Thank you for watching, and please subscribe to get more videos.